Okay, now we will look at the case of long line model. For the definition, long line model, basically the length is more than 250 kilometers, which is more than 150 miles, and line constants are uniformly distributed over the entire length of line. Okay, when we look at the case of the medium line model, we have only one impedance, same like the short line model, and we add the capacitor at the sending end and also at the receiving end. That is for the case of medium line model. But for the case of the long line model, we distribute all the impedance, okay, throughout the transmission line, and also we also distribute the parameter constant of admittance or capacitance Y throughout the transmission line. So from here we can use the ABCD parameter, similar like the case of short and medium line model, but the ABCD parameter becomes more complex. Okay, we will see how complex is it. And the expression for the voltage and current at any point along the line could be derived. So means that we can derive what is the voltage at here, okay, the current at here, voltage and current at this point, and also voltage and current before the receiving voltage. Okay. So let's look at the simplified equivalent circuit. So from this circuit, we have the sending voltage here, and then sending current IS. Okay. So the current go throughout all the transmission line. So the current keep changing, that is IS X plus delta X. Okay. The X, the changing of the current, and then the first parameter of first voltage, first portion of the parameter constant, we got Vx plus delta X. Okay, and Y delta X is nothing but the admittance or the capacitance here, or the first capacitance after the sending voltage, and then the current travel through the line impedance, that is Z delta X, and we have the current, final current, that is Ix before the receiving end. Okay, while final voltage before receiving end is Vx. Here we assume that all the admittance will be the same, that is Y delta X, through the whole transmission line system. And the current before the receiving voltage is IR. Okay, this is receiving voltage IR. Delta X is nothing but the difference between the first voltage or first constant that we give after the sending end and before the receiving end. Okay, L is nothing but the transmission distance. Okay, so from this equation we can make the first equation, okay, at this point, okay, Vx plus delta X, okay, in series, Vx plus delta X in series is nothing but Z delta X Ix plus Vx. So Vx is here, and Z delta X is the voltage at the, so the Z delta X Ix is the voltage at the transmission line. So we can simplify this equation. So we bring delta X here. So we got Vx plus delta X minus Vx over delta X equal to Z Ix. So for delta X equal to 0, so we got dVx over dx equal to Z Ix. So this is equation 1. Then for current, okay, Ix plus delta X is nothing but the current here at this point. Okay, we use KCL. So IS x delta x, or IX delta x equal to IX. IX is current here, same in the transmission line, plus y delta x, V delta plus, sorry, Vx plus delta x. Okay, the current at this point, the current go to the admittance. So we can simplify by bringing delta x here. Okay, and then while delta x approaching to 0, so we got the differentiation of dIx over dx equal to y dx. So this is equation number 2. So we can replace 2 into 1. Okay, we replace 2 into 1, this equation into this equation. So we got that d square dx, okay, over dx square equal to z dix over dx, or zy dx. Okay, zy dx. So this is equation number 3. From equation number 3, that is d square vx over dx square equal to zy dx. Okay, and there is a propagation constant, that is gamma here. Gamma square equal to zy. Okay, here gamma square equal to zy. So our equation will be d square vx over dx square equal to gamma square vx. Okay, by bringing to this part, so we got d square vx over dx square minus gamma square vx equal to 0. And from the second order differential equation, we can find that vx equal to a1, okay, a1 exponent gamma x plus a2 exponent minus gamma x. Okay, gamma is nothing but the propagation constant. Can also be simplified into alpha plus j b beta, also same like square root z over y, also same like square root r plus j omega l times g plus j omega c. Alpha is the attenuation constant, and beta is the phase constant, that is radian per unit length. Okay, from 1, okay, from equation 1 we have dvx over dx equal to zix. Okay, so for vx equal to this equation, okay, that is a1 e gamma x plus a2 e minus gamma x. Okay, this is actually, this voltage Vx is the voltage before the receiving voltage. So for this we can get the Ix equal to 1 over z dvx over dx, okay, equal to 1 over z gamma a1 e gamma x minus gamma a2 exponent minus gamma x. Okay, while Ix equal to y gamma gamma over z, so we just bring this gamma out from this equation. So we got Ix equal to gamma over z a1 exponent gamma x minus a2 exponent minus gamma x. Okay, since gamma square equal to zxy, so we can replace this to the equation. So we got Ix equal to this equation. Okay, and further we can replace zc equal to square root of z over y. So we got Ix equal to 1 over zc. Okay, a1 exponent gamma x minus a2 exponent minus gamma x. So this is the current before the receiving current, and zc is nothing but the characteristics impedance. Now we have the value of Vx and also value of Ix. Okay, when x equal to 0, okay, we first recall that we have this value Vx, and we have the value for current, that is Ix. Okay, so for x is 0, so Vx can further be simplified when x is converted to 0 here. So exponent 0 will be 1. So we got Vx equal to A1 plus A2. Okay, similarly for IR, okay, Ix or IR, we got IR equal to 1 over Xc A1 minus A2 for the case of x equal to 0. Okay. So further we simplify the Ix equal to IR equal to 1 over Zc. Okay. A2 is nothing but VR minus A1. Okay. A2 is VR minus A1. So we replace this A2 by VR minus A1. So we got 1 over Zc A1 minus VR plus A1 here. So further simplify, we got 2A1 minus VR over Zc. So now we got A1 equal to VR Zc IR over 2. Okay. Okay, if we replace A1, okay, A1 is nothing but VR minus A2. So A1 is VR minus A2. Okay. So we got Ix or IR equal to 1 over Zc VR minus A2 minus A2. So we got VR minus 2A2 over Zc. So A2 equal to VR minus Zc IR. Okay. So we can replace the value of A1 and A2. So A1 we can replace to this one, A2 to this one. So we got Vx, okay, equal to A1 of VR plus Zcir over 2 exponent gamma x, okay, plus VR minus Zcir over 2 exponent minus gamma x. Okay, this is A1, this is A2 from this equation. Also, we can replace to the current equation. So we got current Ix equal to A1, okay, that is VR over Zc plus IR over 2 exponent gamma x, and also VR minus Zc minus IR over 2 exponent minus gamma x. Okay, so we have the equation now for the voltage and the current. So further we simplify, okay, by taking out the VR, IR from the voltage, so we can get Vx equal to E gamma x plus exponent minus gamma x over 2 VR plus Zc exponent gamma x minus exponent gamma x over 2. Okay, so if we look at our ABCD model, so V equal to A VR plus VIR, so this one can be represented as A and this one can be represented as B. Okay, similarly for current Ix, okay, we can take out VR and IR from the equation. So we got C equal to 1 over Zc exponent gamma x minus exponent minus gamma x over 2, while D equal to A parameter, that is exponent gamma x plus exponent minus gamma x over 2. Alright. In terms of hyperbolic function, so we can represent the voltage and the current into cos hyperbolic gamma x VR plus Zc sin hyperbolic gamma x IR. Okay. While for the current Ix equal to 1 over C sin hyperbolic gamma x VR plus cos hyperbolic gamma x IR. So we can set x as the distance L. So Vx will be VL equal to V sending. Okay, Ix equals to IL equal to I sending. Now we get the sending voltage is nothing but cos hyperbolic gamma L VR plus Zc sin hyperbolic gamma L IR, while the sending current is 1 over ZC sin hyperbolic gamma L VR plus cos hyperbolic gamma L IR. So from here we can take out A constant equal to D constant, that is cos hyperbolic gamma L. B constant is ZC sin hyperbolic gamma L, and C is nothing but 1 over ZC sin hyperbolic gamma L, where AD minus BC equal to 1. Okay. So we can represent the nominal pi model for a long line in terms of sending voltage and sending current to this formula. Okay. If you recall that for the medium line model, we use A constant, that is 1 plus ZY over 2. So for long model, we represent Z into Z prime and admittance Y into Y prime. Okay. So same for the case of B, that is B equal to Z prime. Okay. C equal to Y prime, Y plus Z prime, Y prime over 4. And D equal to A, that is 1 plus Z prime, Y prime over 2. Okay. So by comparing the B constant with hyperbolic function, okay, B constant is B equal to ZC sin H gamma L. Okay, we can convert this B equal to Z prime here. So Z prime equal to ZC sin hyperbolic gamma L. So ZC is equal to square root of Z over Y. Okay. And further elaborate this equation, we got square root of Z sin hyperbolic gamma L over gamma over square root Z. So finally we got Z prime equal to this equation, which is Z prime equal to Z, that is the impedance, sin hyperbolic gamma L over gamma L. Okay, we got Z prime. Now we want to find Y prime over 2. Okay, we can compare the A constant, okay, into the hyperbolic function. Okay, that is 1 plus Z prime Y prime over 2 equal to cos hyperbolic gamma L. Okay, this is the constant for A and D. Okay, and then we can also replace Z prime equal to this equation to this Z prime. Okay, so if we look at this one, we can solve the Y prime. Okay, from here the detail is, okay, 1 we bring to this part. Okay, so we got cos hyperbolic gamma L minus 1. So Z prime equal to Z sin hyperbolic gamma L. Y prime is Y prime over 2 gamma L. So further, we simplify this equation. Okay, sin hyperbolic, we bring it here. So we got Z Y prime over 2 gamma L equal to cos hyperbolic gamma L minus 1 divided with sin H gamma L equal to tangent hyperbolic gamma L over 2. Then we simplify Y prime over 2, okay, through this formula. So we got Y prime over 2 equal to Y over gamma. Okay, this is Y, Y over gamma, tangent hyperbolic gamma L over 2. So we have this Z prime, we have this Y prime over 2, so we can find what is A, what is D, B, and also C. So finally, the equivalent pi model for a long transmission line model will be like this, equivalent circuit. Okay, Z prime equal to Z sin hyperbolic gamma L over gamma L. Y prime over 2 equal to Y over 2 tangent hyperbolic gamma L over 2 divided with gamma L over 2. Okay. Now let's look at the example 6.4. We have 250 kilometer distance transmission line, 500 kilowatt, as per phase value of Z 0.0445, J 0.4 ohm, that is ohm per kilometer, and then Y equal to J 4.0 microsiemens per kilometer. So find ABCD parameters or ABCD constant for by model for the long transmission line. Okay. So from the given Z and Y is given. So we can calculate ZC through this equation. ZC equal to square root 2 of Z over Y. So we got the value of 316.7 minus J 17.76. Okay. And then we can calculate the propagation constant gamma equal to square root 2 of ZY. Okay. So we get this value 7.104 times 10 to the minus 5 plus J 0.001267. So once we have ZC, so we can calculate Z prime. Okay, so ZC is this value. Okay, gamma is this value. Okay, L is the distance. It is 250 kilometer. So we can calculate Z prime equal to 10.88 plus J 98.36, and also we can calculate the Y prime by using the ZC and the same value of gamma here. Okay, and also the distance of 250 kilometer. So we got Y prime equal to J 0.001. So we have this value Z prime, Y prime. So we can calculate the A and D constant. Okay, just use the value of Z prime and Y prime. So we got 0.9504 plus J 0.0055 for A and D constant. B constant is same like Z constant. Okay, while C equal to Y prime 1 plus Z prime Y prime over 4. We got J 0.0009A. Okay, so that's all for today. Thank you very much.